Let's explore x86 assembly language basics. Assembly language interacts directly with the processor hardware. There are several register types, including 32-bit general-purpose registers like EAX, EBX, ECX, and EDX, as well as FPU registers for floating-point operations. Assembly has special instructions for moving data between registers and memory. movzx loads smaller values and fills the upper bits with zeros, making it ideal for unsigned values. movsx loads smaller values but fills the upper bits with the signed bit, preserving negative values. These are crucial when working with different data sizes. Assembly accesses memory using specific syntax. Byte PTR indicates a 1-byte access, while dword PTR accesses a 4-byte value, a 32-bit integer. The addressing modes can use complex expressions like R plus EAX plus EBX to calculate the final memory address. This allows for efficient array and data structure manipulation. Let's examine a common assembly operation, adding array elements. First, we use movzx to load 1 byte from the array and 0 extend it to a 32-bit value in EDX. Then, we add this value to our sum accumulator in ECX. This pattern is frequently used to process array data one element at a time. Assembly language doesn't have structured loop statements like high-level languages. Instead, loops are created using conditional jumps. Here's a typical loop pattern. Initialize a counter, compare it to a limit, conditionally jump to the end if the condition is met, execute the loop body, increment the counter, and jump back to the comparison. This flow control pattern is the foundation of all loops in assembly. The x86 FPU, floating point unit, handles floating point calculations with its own set of instructions and registers. It uses a stack-based architecture with registers named ST0 through ST7. Common FPU instructions include FLD to load values, FMUL for multiplication, FA for addition, SUB for subtraction, and FSTP to store and pop values from the stack. The FPU stack operates as a last-in, first-out data structure. Let's examine a practical example, calculating the height of a projectile using the formula h equals v0t minus a half gt squared. This formula calculates height based on initial velocity, time, and gravity. The steps are: calculate vt, calculate half gt forward, and subtract the second term from the first. Here's the assembly implementation using FPU instructions. We first load v0 and multiply it by time. Then we duplicate this value and multiply by time again to get t squared. Next, we load g and multiply it by t squared. We load 1.0 twice and add them to get 2, then divide to get 0.5. Finally, we multiply by g star and t squared and subtract from v0 star t to get our height. The FPU stack manages all these intermediate calculations efficiently. Let's focus on the important FLD-ST0 operation used in the code. This instruction duplicates the top value on the FPU stack. Before the instruction, ST0 contains 5.0. After executing FLD-ST0, the value is duplicated, and the original elements shift down. This duplication is crucial when we need to use the same value in multiple calculations while preserving the original. To summarize the key assembly language concepts, we've covered the different register types, including general-purpose registers and FPU registers. We've explored memory access techniques with size specifiers and complex addressing modes. We've learned about data movement instructions like movzx and movsx for handling different data sizes. And we've examined FPU operations with their stack-based architecture for floating-point calculations. Assembly programming gives you direct control over hardware resources, but requires careful understanding of these low-level concepts.